This is the second AP Chemistry lecture on reaction kinetics. We're looking specifically at the mathematical relationship between rate and concentration, rate laws, first and second order reactions, and half-lives. The rate can depend on the concentration. We know that that can happen because as the concentration diminishes when the reaction is going on, the reaction rate goes down. Therefore, the rate is dependent on the concentration of the reactants. Here are some questions that come to mind. Is this dependence always the same? Does it depend on the concentration of any reactant? And what can we learn from the dependence? Here is a graph, such as we've seen before, of concentration versus time of reactants and products. Now, how do we determine the relationship between rate and concentration of reactants in the lab? We measure the initial rate of a chemical reaction, or the rate after a couple of seconds. We change the concentration of one of the reactants, and then we measure the new rate of reaction, looking for a change. After thorough study, we do the same with the concentration of the other reactant. For example, ammonium ions react with nitrite ions at 25 degrees Celsius. So we mix ammonium chloride with sodium nitrite in water at a constant temperature. This is the reaction. Nitrogen gas is formed. We measure the initial rate of nitrogen generation. If we do that, and then control on the nitrite, as you see here, we keep that nitrite concentration constant, and we change the ammonium concentration from 1 to 2 to 4 to 6, we can see a change in the rates here. If we study that, then we see that the nitrite concentration being constant, as the ammonium concentration goes up, the rate of the reaction goes up in a linear fashion. The rate of reaction is directly proportional to the concentration of the ammonium ion. Therefore, we can say that with nitrite constant, the rate of reaction is equal to some constant times the ammonium concentration. If we then study the effect of nitrite concentration, keeping ammonium constant, we measure the concentration and the rate here. We do the graph, and we see that the rate of reaction is directly proportional to the concentration of the nitrite with constant ammonium concentration. So we can write that the rate of reaction is equal to some constant 2 times the nitrite concentration, the ammonium being constant. That means, therefore, that the rate of reaction is equal to some other constant times the concentration of nitrite times the concentration of ammonium. This equation is called a rate law. It enables us, if we know the constant here, it enables us to find the rate of reaction if we know the concentration of nitrite and ammonium, or if we know the concentration of nitrite and the rate and the constant, we could solve for the concentration of ammonium ion. The constant, K, is called a rate constant. Let's calculate the rate constant by plugging in numbers from our table. Constant is equal to the rate divided by the product of the two concentrations. If you do that on your calculator, you will see that the rate constant is 2.7 times 10 to the negative 4th reciprocal mole reciprocal seconds, or moles per second. Every other set of data is going to give the same constant. This is the empirical method for calculating rate constants for any reaction. Given the rate constant and the rate law, we can calculate the rates of reaction for any set of concentrations. Naturally, we need to do it at the temperature at which the original constant was measured. So, if you double the concentrations of both of these two reactants, ammonium and nitrite, what will happen to the rate? it will quadruple. Now, rate laws for nearly all reactions are of a specific algebraic form. The rate is equal to a constant times the reactant 1 concentration to a power m times the reactant concentration 2 to an n power times, and again, if there's three or four reactants, we just keep on going. The exponent m is the order of reaction in reactant 1. The exponent n is the order of reactant 2 for this reaction. The sum of all the exponents is the overall order of the reaction, overall reaction order. What's the reaction order for this reaction? Well, the rate law has K times the nitrite to the first power and the ammonium to the first power, and therefore the reaction order is 1 plus 1 or 2. The reaction is second order overall. What's the reaction order here if the rate is equal to K times the concentration of the dinitrogen pentoxide? What's the reaction order here if the rate is equal to a constant times the concentration of the trichloromethane times the concentration of the chlorine to the 1/2 power? And finally, here with the hydrogen iodide, hydrogen and iodine each to the first power. Now remember, you cannot predict rate laws or reaction order from a balanced equation. You must do it empirically. It has to have reaction data. Now a note on the units. Rate constants are derived from the rate law. Therefore, the rate law depends on the empirical data. That means that rate constants do not have a fixed dimension. So don't get hung up on this. The rate constant is just a way to make the equation work. Now, what does each reaction order mean? Well, a reaction is zero order in a reactant Z, then the reaction rate does not depend on Z. The reaction goes as long as some Z is present, but it doesn't depend on its concentration. Therefore, Z does not appear in the rate law. First order in reaction F. The reaction rate is directly proportional to the concentration of F. The rate is equal to K times the concentration of F. If you double F, you double the rate. If you triple F, you triple the rate. Reaction is second order in reactant F. Reaction rate is proportional to F squared. The rate is equal to some constant times F squared. If you double the F, you quadruple the rate. If you triple the F, the rate will increase 9-fold. So let's do a sample exercise. The initial rate of a reaction, A plus B reacts to form C, is measured for different starting concentrations of A and B, with the results given here. As you can see, we hold A constant between these two runs, and B constant between the first and the third runs. What is the rate law? The magnitude of the rate constant and the rate of the reaction under these two circumstances. Okay, let's do the rate law. First, we note that changing the concentration of B has no effect on the rate of the chemical reaction. So the reaction is zero order in B. Next, we note that doubling the concentration of A quadruples the rate of the chemical reaction. Therefore, the reaction is second order in A. The rate law, therefore, is K times concentration of A squared times the concentration of the B to the 0 power. Therefore, K times A squared is all you would actually write. Let's do the magnitude of the rate constant. Well, if this is the rate law, then K is equal to the rate for any given concentration divided by the square of that concentration. So we'll use one of them. 16 times 10 to the negative fifth is the rate, and that was when each was 0.2 molar, and therefore the rate constant is 4.00 times 10 to the negative third reciprocal moles, reciprocal seconds. Now let's calculate the rate when A is 0.05 and B is 0.1. Well, simply plug in things in. K is equal to 4.0 times 10 to the negative third. Therefore, the rate is that times 0.050 squared, or 1 times 10 to the negative fifth. Now, there's another exercise. Suppose a reaction is found to depend on the concentration of the hydronium or hydrogen ion, and we have the initial rates here and the initial hydrogen ion concentrations here. What's the order of reaction in the hydrogen ion concentration? What will be the reaction rate when the hydrogen ion concentration is 0.4? Now this is a little tricky, so watch carefully. This looks so much like just a plain old Boyle's law, experiment data, and graph that we have to see if this is actually a reciprocal relationship. And when we do graph the reciprocal of the rate versus the hydrogen ion concentration, we get an extremely straight line. So the rate is directly proportional to the reciprocal of the concentration. The reaction order then is -1. At 0.4 molar then, the rate is half that at 0.2 molar, or 0.08 to the negative seventh, 10 times 10 to the negative seventh moles per second. Now, differential calculus can teach us the relationship between rate of reaction and duration of reaction. For a first order reaction, where A determines the rate, we have this relationship. The rate is the negative change in the concentration of the reactant as a function of time, or K times the concentration of A. It can be shown that there is a relationship between the initial concentration of A at any given at time 0, and A at any later time, A sub t. Here's the relationship. The natural log of A at any given time t minus the natural log of A at time 0 is equal to minus K times t. Remember, this is the rate law constant. Or you could also say the natural log of A at time t over A at time 0, again, natural log of this ratio, is equal to K times t. Rearranging, we can get the natural log of A at time t equal to minus kt plus the natural log of A at time 0. And hang on. If we have that relationship, we see this is of the form y equals mx plus b. This is going to be a constant, isn't it? This is a slope, and this is time. So the quantity m is the slope minus k, and b is the intercept, the natural log of our initial concentration of A. Therefore, for a first order reaction, a graph of the natural log of the concentration versus time will give a straight line. The slope of the line is the negative of the rate constant, and the y-intercept is the natural log of the initial concentration of A. So here's a sample exercise for you to do. You can stop the video and do it. And here's the solution.